the deepest night, far beyond our atmosphere, beyond our solar system, beyond even our galaxy, lies the vast tapestry of existence we call the universe. For millennia, humanity has gazed upward, wondering about the nature of this cosmic expanse. Is it infinite? Does it have an edge? And perhaps most fundamentally, does it have a shape? The universe is vast, but it also has a shape, one that guides its destiny. But is that shape fixed, or does it change with time? Tonight, we explore the form of everything and the subtle dance of cosmic geometry. When Einstein revealed that massive objects bend the fabric of space and time around them, he was not just describing gravity in a new way. He was telling us something profound about the nature of the cosmos itself. Space is not just an empty stage where cosmic events unfold. It is more like a living canvas, one that stretches, warps, and perhaps fundamentally changes as time flows forward. Throughout human history, we have tried to map the heavens, to place ourselves within the grand architecture of existence. The ancient Greeks imagined crystalline spheres, medieval scholars debated finitude versus infinity, and now modern cosmologists probe the universe with sophisticated instruments and mathematics. But the question remains, what is the shape of everything? And is that shape evolving as the universe ages? To begin this journey, we must first understand what we mean by shape when discussing something as vast and mysterious as the universe itself. We must learn to see with the mind what the eye cannot perceive, the geometry of reality itself. The stars we see twinkling in the night sky exist within a framework, a structure that physics is still striving to fully comprehend. As we look deeper into space, we are also looking back in time, witnessing light that has traveled for billions of years across an expanding cosmos. This cosmic light show brings us clues about the underlying architecture of everything. Consider for a moment that the universe might be curved, with light following paths that bend ever so slightly over immense distances. Or perhaps it is perfectly flat, with light traveling in absolutely straight lines from the beginning of time until now. These possibilities speak to the fundamental nature of space itself, a nature that may be slowly transforming as cosmic eons pass. What shape would give rise to the universe we observe? And more intriguingly, has this shape remained constant since the Big Bang, or is it gradually morphing into something else entirely? These questions touch not just on physics and astronomy, but on the deepest philosophical inquiries about existence itself. Picture yourself floating in the void of deep space, gazing outward in all directions. The galaxies around you form patterns, cosmic structures arranged in a web-like formation stretching across billions of light years. But is this web infinite in all directions? Does it curve back upon itself like the surface of a sphere, or does it stretch outward forever, growing thinner and more tenuous with distance? The answer lies in the subtle geometry of space itself, a geometry that may be slowly changing as the universe expands. When we speak of the shape of the universe, we are not referring to its outline against some external backdrop. There is no outside to the universe, no external vantage point from which to view its form. Instead, we mean its intrinsic geometry, the rules that govern how space itself behaves, how distances work, how parallel lines interact over cosmic scales. Imagine drawing a giant triangle across the cosmos, with each vertex marking a distant galaxy. If space is flat, the angles of this triangle would sum to exactly 180 degrees, just as they do on a flat piece of paper. But if space is curved, this sum would differ. In a positively curved universe, like the surface of a sphere, the angles would sum to more than 180 degrees. In a negatively curved universe, like a saddle shape, they would sum to less. These differences, though subtle, reveal the underlying shape of reality itself. The ancient cosmologists viewed the heavens as perfect and unchanging, with celestial bodies embedded in crystalline spheres rotating eternally around Earth. Today, we know the cosmos is neither perfect nor unchanging. It breathes and evolves, expands and transforms. The question is not whether the universe changes, but how it changes, and what its ultimate fate might be. If the universe is curved like a sphere, but expanding, is it becoming less curved over time? Imagine a balloon inflating, its surface becoming flatter from the perspective of a tiny inhabitant as it grows. Or perhaps the universe began nearly flat and is becoming more curved as mysterious forces pull and push on its fabric. These are not merely abstract mathematical curiosities, but questions about the destiny of everything that exists. The shape of the universe is intimately connected to its fate. Will it expand forever, growing ever colder and more diffuse? Will it eventually stop expanding and begin to contract, galaxies rushing toward one another in a great cosmic collapse? Or will it reach some equilibrium state, balanced between expansion and contraction? The answers depend on the geometry of space and the forces that act upon it. As we drift through the cosmos on our tiny planetary home, we are part of this grand geometric dance. The shape of space influences the paths of light rays that reach our telescopes, the trajectories of galaxies as they move through the cosmos, and perhaps even the fundamental constants that govern physics itself. We are not merely observers of cosmic geometry, but participants in its unfolding story. Our journey tonight takes us from the smallest scales of quantum geometry, where space itself might be grainy and discrete, to the largest scales of the observable universe and beyond. We will explore how astronomers measure the curvature of space, how physicists model its evolution, and how philosophers contemplate the meaning of it all. We will gaze into the deepest mysteries of existence and consider the possibility that our universe might be just one shape among many in a vast multiverse of alternative geometries. Join us now as we embark on this exploration of cosmic form, this meditation on the architecture of everything. For in understanding the shape of the universe and how it changes, we come closer to understanding our place within the greatest structure of all, reality itself. To know the universe, we must first understand shape. Geometry, the mathematics of space and form, gives us the language to describe the cosmos. But cosmic geometry operates on scales far beyond everyday experience, where intuition often fails us, and mathematics becomes our most reliable guide. Imagine an ant walking on the surface of a sphere, like our Earth. To the ant, the world appears flat in its immediate vicinity. It can walk in straight lines, make right angles, and measure distances just as it would on a flat plane. But if that ant could somehow see the bigger picture, it would realize its flat world is actually curved when viewed from outside. Our universe presents us with a similar situation, albeit vastly more complex. We are embedded within the very geometry we are trying to measure. Just as the ant cannot easily perceive the global curvature of the Earth, we cannot directly observe the overall shape of the cosmos. Cosmologists typically describe three possible geometries for our universe: flat, closed, or open. In a flat universe, parallel lines remain parallel forever, and the familiar rules of Euclidean geometry that we learn in school hold true even at the largest scales. The sum of angles in a triangle equals exactly 180 degrees. This universe would extend infinitely in all directions. In a closed universe, space curves back on itself, like the surface of a sphere. Parallel lines eventually converge, and the sum of angles in a triangle exceeds 180 degrees. If you could travel far enough in one direction, you might eventually return to your starting point, having circumnavigated the entire cosmos. In an open universe, space curves in the opposite way, like a saddle or the surface of a trumpet. Parallel lines gradually diverge, and the sum of angles in a triangle is less than 180 degrees. This universe would also be infinite, but with a different kind of infinitude than the flat case. These three possibilities, flat, closed, or open, correspond to three possible fates for our cosmos. A precisely flat universe would expand forever, but at an ever-decreasing rate. A closed universe might eventually stop expanding and begin contracting, leading to what physicists call a big crunch. An open universe would expand forever, with galaxies moving apart at an ever-increasing rate. The true shape of our universe depends on its density, the amount of matter and energy it contains relative to a critical value. If the density equals the critical value, the universe is flat. If it exceeds this value, the universe is closed. If it falls short, the universe is open. But identifying the shape of the cosmos is not as simple as measuring its density at one moment in time. The universe is dynamic, with forces pulling matter together and mysterious dark energy pushing space apart. These competing influences cause the shape of space to evolve. Let us delve deeper into what we mean by the geometry of space. In the early 20th century, mathematicians explored non-Euclidean geometries. systems where the familiar rules of flat space no longer apply. They discovered that consistent mathematical frameworks could describe spaces with constant positive curvature, like spheres, or constant negative curvature, like saddles. Einstein incorporated these mathematical insights into his theory of general relativity. In this revolutionary framework, gravity is not a force in the conventional sense, but a manifestation of space-time curvature. Massive objects like stars and planets create dents in the fabric of space-time, causing nearby objects to follow curved paths that we interpret as gravitational attraction. This principle applies not just locally, around individual massive bodies, but globally, to the universe as a whole. The total distribution of matter and energy throughout the cosmos determines its overall curvature, its fundamental shape. To understand cosmic geometry more intuitively, let us consider some thought experiments. Imagine drawing an enormous circle in space. In flat geometry, the circumference of this circle would be exactly 2 times pi times the radius, just as we learned in school. In a positively curved space, like a sphere, the circumference would be less than this value, as if the measuring tape were being squeezed. In a negatively curved space, the circumference would exceed this value, as if the measuring tape were being stretched. Similarly, consider 2 spacecraft traveling on parallel trajectories. In flat space, they would maintain the same distance from each other indefinitely. In positively curved space, they would gradually converge. In negatively curved space, they would slowly drift apart, despite both traveling on what they perceive as straight lines. These effects are extremely subtle on the scales we can directly observe, which is why determining the geometry of the universe requires precise measurements and sophisticated analysis. We cannot simply look at the universe and see its curvature. We must infer it from careful observations of light paths, cosmic structures, and the remnant radiation from the early universe. The shape of space affects not just how objects move, but how light travels. In a curved universe, light follows geodesics, the shortest paths between points in curved geometry. These paths can create optical illusions from our perspective, making distant objects appear in unexpected positions, or even creating multiple images of the same object, a phenomenon known as gravitational lensing. At the largest scales, the curvature of space might cause us to see patterns in the distribution of galaxies that reflect the underlying geometry. If the universe were positively curved and sufficiently small, we might even see the same objects in different directions, as light from them reaches us by traveling different paths around the curved cosmos. But discussing the shape of the universe becomes even more complex when we consider that it exists not just in space, but in space-time. The universe is not a static 3-dimensional object, but a dynamic 4-dimensional entity evolving through time. Its shape encompasses not just its spatial geometry at one moment, but the entire history of its expansion and evolution. Mathematicians describe the space-time geometry of the universe using what they call the metric, a mathematical object that encodes how distances and times relate to each other throughout the cosmos. The metric of our universe appears to be well described by what cosmologists call the Friedmann-Lemaitre-Robertson-Walker metric, a solution to Einstein's equations that describes a homogeneous, isotropic universe, one that looks roughly the same in all places and all directions. This metric contains a term called the scale factor, which describes how distances in the universe change with time. As the universe expands, the scale factor increases, causing galaxies to move apart. The rate of change of this scale factor is what we observe as the expansion of the universe. But the scale factor alone does not tell us everything about the shape of space. The spatial component of the metric can still represent flat, closed, or open geometry, independently of how the scale factor evolves. Even as the universe expands, its fundamental shape, whether flat like a plane, closed like a sphere, or open like a saddle, can remain the same, at least in a relative sense. However, the evolution of the scale factor can affect the curvature. In the early universe, during a period of rapid expansion called inflation, any initial curvature would have been stretched out, making the observable universe appear very close to flat, regardless of its original geometry. This is similar to how a small section of a balloon appears increasingly flat as the balloon inflates. The tools of topology, the mathematical study of shapes and spaces, allow us to describe even more exotic possibilities for the geometry of the cosmos. Our universe might have a complex topology, like a three-dimensional analog of a torus, a donut shape. In such a universe, space would still appear locally flat, but would connect back to itself in non-trivial ways. Imagine a video game where exiting one side of the screen causes your character to reappear on the opposite side. The surface of the screen appears flat, but topologically, it behaves like a torus. Similarly, our universe might have a topology that causes light to wrap around in unexpected ways, creating cosmic illusions and patterns that could, in principle, be detected through careful observation. Some cosmologists have even suggested that our universe might have a multi-connected topology, with multiple paths between the same points in space. This could create a cosmic hall of mirrors effect, where we see the same objects repeated in different directions and at different distances. Searches for such patterns in the cosmic microwave background, the ancient light from the early universe, have so far come up empty, but they represent an intriguing possibility. The mathematics to describe these complex shapes exists, albeit in abstract form. Manifolds, the mathematical structures used to model the universe, can have all manner of exotic geometries and topologies. The challenge lies in connecting these abstract possibilities to observable reality, in figuring out which mathematical model best describes the universe we actually inhabit. This brings us to a philosophical question. Is the universe shaped by mathematics, or is mathematics merely our attempt to describe the universe? Do mathematical structures exist independently of physical reality, with our universe somehow embodying certain mathematical forms? Or is mathematics simply a human construct, a language we have developed to model the patterns we observe? The renowned physicist Eugene Wigner once wrote about the unreasonable effectiveness of mathematics in describing the natural world. It seems almost miraculous that abstract mathematical concepts, often developed without any reference to physical applications, turn out to be precisely the tools needed to describe the deepest structures of reality. Perhaps this hints at something profound about the nature of existence itself, that at its core, reality has a mathematical character, that the shape of the universe is, in some sense, a mathematical shape. This perspective, known as mathematical Platonism, suggests that mathematical objects and structures have an existence independent of human minds, and that physical reality is, in some sense, an incarnation of these abstract forms. Others take a more pragmatic view, seeing mathematics as simply the most effective language humans have developed to describe patterns and regularities in nature. In this view, when we talk about the shape of the universe, we are not discovering some pre-existing mathematical reality, but constructing models that usefully predict our observations. Regardless of one's philosophical stance, it is clear that mathematics provides our best tools for understanding cosmic geometry. From Einstein's field equations to the latest computer simulations of cosmic evolution, mathematical models guide our exploration of the universe's shape. As we continue our journey, we will see how these abstract geometric concepts connect to observable reality, how astronomers and cosmologists measure the curvature of space, and how the shape of the universe influences its past and future evolution. But first, let us pause to appreciate the profound insight that space itself has shape, that the void between objects is not nothing, but a structured, geometric entity with properties that can be measured and studied. The ancient Greeks believed that nature could be understood through geometry, that at its core, reality had a mathematical character. Modern physics has vindicated this intuition in ways they could never have imagined. The shape of the universe is not a metaphor, but a physical reality, one that guides the dance of galaxies and the fate of everything that exists. As we drift into sleep tonight, may we carry with us this profound realization that we exist within geometry, that the vast cosmos around us has form and structure, and that this form may be slowly evolving as the universe expands and ages. In contemplating the shape of everything, we touch upon one of the deepest mysteries of existence, a mystery that continues to unfold as our understanding grows. Light bends, and through it, we glimpse the cosmos's form. Throughout human history, we have gazed at the stars, wondering about our place in the universe. But only in the last century have we developed tools powerful enough to actually measure the shape of the cosmos itself. This quest to determine whether the universe is flat, closed, or open has driven the development of ever more sophisticated instruments and observational techniques. The challenge of measuring cosmic geometry is immense. We cannot step outside the universe to observe its shape. We cannot even travel to distant regions to take direct measurements. Instead, we must infer its geometry from the limited information that reaches our telescopes, primarily in the form of light that has traveled across vast cosmic distances. Let us begin with one of the most important tools for probing the universe's shape: the cosmic microwave background radiation, often abbreviated as CMB. This faint glow, permeating all of space, is the afterglow of the Big Bang itself, the oldest light in the universe. It began its journey when the cosmos was just 380,000 years old, a mere infant in cosmic terms. The cosmic microwave background radiation provides us with a snapshot of the early universe, a time when the cosmos was simpler and more uniform than it is today. By studying minute temperature variations in this radiation, cosmologists can infer the geometry of the space through which it has traveled. These temperature variations form a pattern of hot and cold spots across the sky. The typical size of these spots depends on the geometry of space. In a flat universe, the spots would have a characteristic angular size that cosmologists can predict from theory. In a closed, positively curved universe, the spots would appear larger than this prediction, as if seen through a magnifying lens. In an open, negatively curved universe, they would appear smaller, as if seen through a diminishing lens. Sophisticated space observatories like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have mapped these temperature variations with extraordinary precision. Their measurements suggest that our universe is remarkably close to flat, with any curvature being less than about 0.5%. This flatness is one of the most important discoveries in modern cosmology. But the cosmic microwave background is not our only window into cosmic geometry. The distribution of galaxies throughout space also contains clues about the universe's shape. Galaxies are not scattered randomly throughout the cosmos, but form a vast cosmic web with clusters and superclusters, connected by filaments and separated by enormous voids. The statistical properties of this cosmic web, how galaxies cluster together at different scales, are influenced by the underlying geometry of space. By conducting enormous surveys of galaxy positions, astronomers can measure what they call the power spectrum of galaxy clustering, essentially a mathematical description of how galaxies group together at different distances. For instance, there is a characteristic scale in the universe, known as the Baryon Acoustic Oscillation Scale, that acts as a kind of cosmic ruler. This scale, about 500 million light-years in today's universe, corresponds to the maximum distance that sound waves could travel in the early universe before cosmic structure formation began. It appears as a slight preference for galaxies to be separated by this particular distance. If space is curved, this cosmic ruler would appear distorted when viewed from different angles and distances. By measuring this scale across vast cosmic distances, astronomers can infer the geometry of the space between galaxies. So far, these measurements also support the conclusion that our universe is very nearly flat. Another powerful technique for probing cosmic geometry involves gravitational lensing, the bending of light as it passes near massive objects. Einstein predicted this effect, which was first confirmed during a solar eclipse in 1919, when stars near the edge of the sun appeared slightly out of position due to the sun's gravitational field bending their light. On cosmic scales, entire galaxy clusters can act as gravitational lenses, creating multiple images or distorted arcs of more distant galaxies behind them. The exact pattern of these lensed images depends not just on the mass of the lensing cluster, but also on the geometry of the space between the cluster, the lensed galaxy, and us as observers. By studying many examples of gravitational lensing across the universe, astronomers can build up a picture of how light paths bend on cosmic scales, providing yet another test of the universe's shape. These measurements too suggest a universe very close to flat. Time delay cosmography is a specialized form of gravitational lensing study that measures how long it takes light to travel along different paths around a massive object. When a distant quasar is gravitationally lensed, creating multiple images, variations in the quasar's brightness appear in these images at different times. As the light has traveled along paths of different lengths, these time delays depend on both the mass distribution of the lens and the geometry of space, providing a unique probe of cosmic curvature. One of the most straightforward ways to test the geometry of the universe is to measure its density and compare it to the critical density needed for a flat universe. If the total density of matter and energy equals this critical value, the universe is flat. If it exceeds this value, the universe is closed. If it falls short, the universe is open. Astronomers have measured the density of ordinary matter by observing how much light it emits or absorbs. They have inferred the presence of dark matter through its gravitational effects on visible matter, and they have detected the influence of dark energy through its effect on the universe's expansion rate. Adding up all these components gives a total density remarkably close to the critical value for a flat universe, providing yet another line of evidence for cosmic flatness. The accelerating expansion of the universe, discovered in 1998 through observations of distant supernovae, also contains information about cosmic geometry. The exact relationship between a supernova's distance and its redshift, a measure of how much the universe has expanded since the supernova's light began its journey, depends on the curvature of space. These measurements, which earned their pioneers the Nobel Prize in Physics, not only revealed the surprising acceleration of cosmic expansion, but also supported the picture of a nearly flat universe. Despite all these lines of evidence pointing to a flat universe, measuring the exact curvature remains an enormous challenge. The effects of curvature are most pronounced at the largest scales, but our observations are limited to the observable universe, the finite region from which light has had time to reach us since the Big Bang. If the universe is curved only very slightly, we might need to observe a much larger region to detect this curvature definitively. Furthermore, cosmic curvature can be confused with other effects. For instance, if the relationship between distance and redshift in the universe differs from our standard cosmological model for reasons other than curvature, we might misinterpret our observations. This is why cosmologists use multiple, independent methods to measure the universe's shape, looking for consistency across different techniques. Even with our most advanced instruments and techniques, we can only place upper limits on how curved the universe might be. Current observations indicate that if the universe is a sphere, its radius of curvature must be at least 150 times larger than the observable universe. If it is a hyperbolic space, a negatively curved geometry, its characteristic scale of curvature must be similarly enormous. This extreme flatness poses a puzzle for cosmologists. In the standard Big Bang theory, without inflation, the universe would have had to begin with extremely precise conditions to be so flat today. Even tiny deviations from flatness in the early universe would have been amplified over time, leading to a highly curved universe now. The theory of cosmic inflation, a period of extremely rapid expansion in the first fraction of a second after the Big Bang, offers an explanation for this flatness problem, as it would have stretched out any initial curvature, making the observable universe appear flat regardless of its initial geometry. But the question remains, is the universe exactly flat, or just very close to flat? And has its curvature been constant, or has it evolved over cosmic history? To answer these questions, astronomers are developing even more precise measurement techniques and planning new observatories both on Earth and in space. Future galaxy surveys, like those that will be conducted by the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope, will map the positions of billions of galaxies across unprecedented cosmic volumes. These surveys will measure the baryon acoustic oscillation scale with extraordinary precision across different cosmic epochs, tracking how the universe's shape may have evolved over time. New cosmic microwave background observatories, both ground-based and space-based, will map the relic radiation from the Big Bang with even greater sensitivity, extracting the subtle signals of cosmic curvature from the noise of foreground emissions and instrumental effects. Some proposals even call for interferometers in space, linking telescopes across vast distances to achieve the resolution needed to detect the signatures of cosmic curvature in the microwave background. Gravitational wave observatories like LIGO and Virgo, and future space-based missions like LISA, offer a completely new window into cosmic geometry. These instruments detect ripples in space-time created by violent cosmic events like black hole mergers. The pattern of these ripples depends on the geometry of the space through which they have traveled, potentially providing a new and independent probe of the universe's shape. As we wait for these next-generation observatories to come online, Theorists are working to refine our understanding of how different geometries would manifest in observable data. They are developing more sophisticated statistical techniques to extract the subtle signals of cosmic curvature from increasingly precise but inherently noisy measurements. This quest to measure the universe's shape exemplifies the scientific method at its most ambitious. We begin with a question that seems almost philosophical. What is the shape of everything? We develop mathematical models that make testable predictions. We build instruments of astonishing sensitivity to test these predictions. And we continuously refine both our theories and our measurements as we spiral ever closer to the truth. The provisional answer, based on all our observations so far, is that the universe appears to be flat, or very nearly so, on the scales we can observe. This conclusion, though tentative and subject to revision with new data, represents one of the great triumphs of modern cosmology. From our tiny vantage point on a small planet orbiting an ordinary star, humans have managed to measure the geometry of the cosmos itself. But the story does not end there. Measuring the universe's shape at one moment in time is not the same as understanding how that shape evolves. As we will explore in later chapters, the universe is not static, but dynamic, its geometry potentially changing as it expands and evolves. Moreover, the apparent flatness of the observable universe does not preclude more complex geometries on even larger scales, beyond what we can currently observe. Some cosmological models suggest that our nearly flat observable universe might be just a small patch of a much larger cosmos with a more complex geometry, like a small section of a balloon that appears flat to an ant crawling on its surface. There is also the intriguing possibility that the topology of the universe, its global connectivity, might be more complex than its local geometry suggests. A flat universe could still have a non-trivial topology, connecting back on itself in complex ways, like a three-dimensional analog of a video game screen, where exiting one side brings you back on the opposite side. Astronomers have searched for signs of such cosmic connections, looking for paired patterns in the cosmic microwave background or repeating structures in the distribution of galaxies that might indicate a multi-connected topology. So far, no convincing evidence for such cosmic echoes has been found, but the search continues with increasingly sensitive instruments and techniques. As we contemplate these cosmic measurements, it is worth reflecting on the extraordinary achievement they represent. Using light that has traveled across billions of light years, filtered through instruments of remarkable precision, analyzed with sophisticated mathematical techniques, humans have begun to measure the shape of the cosmos itself. We have detected the subtle curvature of space-time around massive objects and placed constraints on the curvature of the universe as a whole. This enterprise connects the largest scales imaginable to some of the smallest, from the cosmos itself to the quantum fluctuations that seeded cosmic structure, from the entirety of space to the subatomic particles that register individual photons in our detectors. It represents a pinnacle of human curiosity and ingenuity, a quest to understand not just our place in the universe, but the very shape of reality itself. As we gaze at the night sky, we are looking not just at distant stars and galaxies, but at the geometry of space itself, a geometry we have begun to measure with increasing precision. The apparent flatness of this geometry speaks to the universe's origins and evolution, hinting at processes like inflation that shaped the cosmos in its earliest moments. But measuring is not the same as understanding. As we move forward in our exploration, we must ask what forces and principles determine this geometry, how it has evolved over cosmic history, and what role it plays in the unfolding story of the universe. The shape of space is not merely a static backdrop, but a dynamic participant in the cosmic drama, influencing and being influenced by the matter and energy that inhabit it. Invisible components govern the universe's shape. As we gaze into the night sky, we see stars, galaxies, and nebulae, the luminous matter that populates our cosmos. Yet this visible universe, as vast and majestic as it appears, is merely the tip of a cosmic iceberg. The majority of the universe consists of components we cannot directly see: dark matter and dark energy, mysterious substances that play crucial roles in determining the shape and evolution of cosmic geometry. The story of dark matter begins in the 1930s, when Swiss astronomer Fritz Zwicky observed the Coma galaxy cluster and noticed something peculiar. The galaxies within the cluster were moving much faster than expected, based on the visible mass present. They moved so quickly that they should have escaped the cluster's gravitational embrace, yet the cluster remained intact. Zwicky proposed that some invisible form of matter, which he called Dunkelmaterie, German for dark matter, must be providing the extra gravitational pull needed to hold the cluster together. For decades, Zwicky's observation remained a curiosity, but in the 1970s, American astronomer Vera Rubin made similar observations while studying the rotation of spiral galaxies. The outer regions of these galaxies were spinning so rapidly that they should have been flung apart, unless some unseen mass was holding them together. Rubin's meticulous measurements provided compelling evidence for Zwicky's dark matter. Today, the case for dark matter has grown even stronger. We observe its gravitational effects throughout the cosmos, from the smallest dwarf galaxies to the largest superclusters. It shapes the cosmic web, the vast network of filaments and voids that stretches across space. It leaves its imprint on the cosmic microwave background, the ancient light from the early universe. And it bends light through gravitational lensing, creating distorted images of distant galaxies. All these observations point to the same conclusion. About 85% of all matter in the universe is dark, invisible to our telescopes, detectable only through its gravitational influence. This dark matter does not interact with light or other forms of electromagnetic radiation, which is why we cannot see it directly. But its gravitational pull affects everything around it, including the shape of space itself. Dark matter plays a crucial role in determining the universe's geometry. By contributing to the overall density of the cosmos, it helps determine whether space is flat, closed, or open. If the universe contains enough matter, including both visible and dark varieties, its gravitational pull could eventually halt and reverse the cosmic expansion, causing space to curve back on itself in a closed geometry. If the density falls below a critical threshold, the universe would expand forever with an open, hyperbolic geometry. For many years, cosmologists attempted to measure the total matter density of the universe to determine its fate. But in the late 1990s, a shocking discovery changed our understanding of cosmic geometry and evolution. Two independent teams of astronomers, studying distant supernovae to measure how the universe's expansion has changed over time, found that the expansion is not slowing down as expected due to gravity. Instead, it is accelerating, as if some mysterious repulsive force is pushing the cosmos apart. This discovery led to the concept of dark energy, an enigmatic component that permeates all of space and drives the accelerating expansion. Unlike dark matter, which clumps under the influence of gravity, dark energy appears to be distributed uniformly throughout the cosmos. It does not dilute as the universe expands, maintaining a constant energy density while the densities of matter and radiation decrease over time. The nature of dark energy remains one of the greatest mysteries in modern physics. The simplest explanation is that it represents the energy of empty space itself, what physicists call vacuum energy, or a cosmological constant. Einstein originally introduced the cosmological constant into his equations of general relativity as a way to achieve a static universe, but later abandoned it when observations revealed an expanding cosmos. Now, it seems, the cosmological constant has returned in a new guise. But the observed value of dark energy poses a profound puzzle. Quantum field theory, our best framework for understanding particles and forces, predicts a vacuum energy many orders of magnitude larger than what we observe. This discrepancy, sometimes called the cosmological constant problem, represents one of the most significant challenges in theoretical physics. Alternative explanations for dark energy include quintessence, a dynamical field that varies across space and time, or modifications to Einstein's theory of gravity on cosmic scales. Some theorists have even suggested that the accelerating expansion might be an illusion, resulting from our position within an unusually large cosmic void. But so far, the simple cosmological constant model provides the best fit to observations, even as its theoretical underpinnings remain mysterious. Together, dark matter and dark energy dominate the energy budget of the universe. Ordinary visible matter, the stuff of stars, planets, and life itself, comprises just 5% of the cosmic total. Dark matter contributes about 27%, while dark energy accounts for the remaining 68%. This composition determines not just the current state of the universe, but its shape and evolution over time. In the early universe, matter dominated over dark energy, and gravity acted to slow the cosmic expansion. But as the universe expanded, matter diluted while dark energy remained constant. Eventually, dark energy overtook matter as the dominant component, leading to the accelerating expansion we observe today. This transition occurred roughly 5 billion years ago, about the time our Sun and solar system were forming. This shift from a matter-dominated to a dark energy-dominated universe had profound implications for cosmic geometry. In a universe containing only matter, the curvature of space would be determined by the density of that matter relative to a critical value. But the presence of dark energy changes this simple picture. Even if the total density of the universe equals the critical value, making space flat, the ultimate fate of the cosmos now depends on the nature and evolution of dark energy itself. If dark energy truly is a cosmological constant, maintaining the same density forever, the universe will expand eternally at an ever-increasing rate. Galaxies beyond our local group will eventually recede so rapidly that their light can no longer reach us. The observable universe will shrink even as the actual universe expands, leaving our distant descendants with an increasingly empty night sky. But if dark energy changes over time, or if it eventually transitions into some other form, the fate of the universe could be different. Some models suggest that dark energy might eventually weaken or reverse sign, potentially leading to a big crunch where the universe collapses back on itself. Others propose a big rip, where dark energy grows so powerful that it tears apart galaxies, stars, planets, and even atoms. The ultimate shape and fate of the cosmos thus depends critically on the nature of its invisible components. The distribution of dark matter and dark energy also affects local geometries within the universe. Dark matter forms a scaffolding around which visible matter congregates, creating a cosmic web of filaments, sheets, and voids. This structure influences how light travels through the universe, creating subtle distortions that astronomers can detect through techniques like weak gravitational lensing. On smaller scales, dark matter forms halos around galaxies, extending far beyond their visible boundaries. These halos modify the local curvature of space, affecting the orbits of stars and the paths of light rays. By mapping these effects, astronomers can chart the distribution of dark matter and gain insights into the true shapes of galaxies, including our own Milky Way. Dark energy, meanwhile, affects the overall expansion rate of space, which in turn influences how cosmic structures form and evolve. In a rapidly expanding universe, gravity has less time to pull matter together, potentially limiting the sizes of the largest cosmic structures. The balance between dark energy's push and dark matter's pull thus shapes the cosmic web itself. The interplay between dark matter, dark energy, and ordinary matter also influences how the universe's geometry evolves over time. In the very early universe, during an inflationary phase that occurred in the first fraction of a second after the Big Bang, space expanded at an enormous rate, stretching any initial curvature to nearly flat. This explains why our universe appears so close to flat today, resolving what cosmologists call the flatness problem. After inflation ended, the universe entered a radiation-dominated era, followed by a matter-dominated era. During these phases, any slight deviation from perfect flatness would have grown over time. If the universe started with slightly positive curvature, this curvature would have increased during the matter-dominated era. If it started with slightly negative curvature, this too would have been amplified. But the transition to dark energy domination changes this picture. In a universe dominated by a cosmological constant, any existing curvature gets diluted rather than amplified. This means that even if the universe is not perfectly flat, any curvature becomes increasingly difficult to detect as cosmic expansion accelerates. This evolution of geometry relates to a broader question. Is the shape of the universe fixed, or can it change qualitatively over time? Could a universe that begins with one type of geometry, say flat or open, transition to another type like closed? The answer depends on the complex interplay between dark energy, dark matter, and the laws of physics on cosmic scales. Some theoretical models suggest that the universe might have undergone phase transitions in its distant past, potentially changing its effective geometry. Others propose that quantum effects in the very early universe could have created a foam-like structure of spacetime, with different regions having different geometries. As the universe expanded, one particular geometry would have dominated our observable region, but others might exist beyond our cosmic horizon. The presence of dark energy raises the possibility of even more exotic scenarios. Some theories suggest that dark energy might represent a false vacuum, a temporary state that could eventually decay to a lower energy state, potentially altering the geometry of space in the process. Others propose that dark energy might be an artifact of extra dimensions of space, whose shape and size could evolve over cosmic time. These speculations point to a profound truth. The universe is not just a static stage on which cosmic drama unfolds, but a dynamic entity whose very shape and structure evolve as it ages. Dark matter and dark energy are not just passive components filling space, but active participants in cosmic evolution, shaping the geometry of reality itself. The quest to understand these dark components has led to ambitious observational programs and experiments. Astronomers use powerful telescopes to map the distribution of dark matter through its gravitational effects on light and visible matter. They track the expansion history of the universe to constrain the properties of dark energy. And physicists search for direct signals of dark matter particles in sensitive underground detectors, hoping to catch rare interactions that might reveal their nature. Next-generation experiments promise even greater insights. The Vera Rubin Observatory will soon begin a decade-long survey of the southern sky, creating the most detailed map yet of dark matter distribution. The Nancy Grace Roman Space Telescope will measure the universe's expansion with unprecedented precision, potentially revealing whether dark energy changes over time. And new generations of particle detectors will search for dark matter with increasing sensitivity, probing theoretical models that have so far eluded experimental tests. These efforts represent one of the greatest scientific adventures of our time, a quest to understand the invisible majority of our universe. The stakes could hardly be higher. Dark matter and dark energy are not merely exotic curiosities, but fundamental components that determine the shape, structure, and ultimate fate of the cosmos. As we contemplate these mysterious dark components, we are reminded of how much remains unknown about the universe, even after centuries of scientific progress. We have mapped the cosmos with incredible precision, charted its expansion history, and developed sophisticated mathematical models of its evolution. Yet roughly 95% of its content remains enigmatic, detectable only through its gravitational influence on the remaining 5%. This humbling realization invites both scientific rigor and philosophical reflection. The dark universe challenges our most sophisticated theories and instruments, pushing the boundaries of human knowledge and ingenuity. But it also reminds us of the vastness and mystery of existence, the profound depths of reality that lie beyond our immediate perception. The universe's shape, it seems, is governed largely by components we cannot directly see, forces we are still struggling to understand. Dark matter pulls, dark energy pushes, and ordinary matter responds to these invisible influences, tracing out patterns that reflect the underlying geometry of space. We, as conscious observers embedded within this cosmic dance, strive to discern its rhythms and rules, even as much of it remains shrouded in darkness. Perhaps this is a fitting metaphor for human existence itself. We navigate a reality whose full nature remains partially hidden from view, inferring deeper patterns from the visible effects they produce, constructing models and narratives to make sense of our observations. The dark universe reminds us that reality may be richer and more complex than our direct experiences suggest, that the visible world is but one facet of a deeper, more mysterious whole. As we continue our exploration of cosmic geometry, we carry this awareness with us, this recognition that the shape of the universe is determined largely by its darkest, most enigmatic components. The visible stars and galaxies that have captivated human imagination throughout history are merely luminous traces of a deeper cosmic architecture, one shaped by the invisible hands of dark matter and dark energy. In our next chapter, we will explore how this shape evolves over cosmic time, how the interplay of visible and dark components drives the unfolding geometry of everything. But for now, let us pause to appreciate the profound insight that the universe's form is governed largely by that which we cannot see, a reminder of how much remains to be discovered about the true nature of reality. The shape of space is not static, it grows and flows. Throughout our journey so far, we have explored the fundamentals of cosmic geometry and how astronomers measure the shape of the universe. We have delved into the mysterious dark components that dominate the cosmic energy budget and influence the curvature of space. Now, we turn our attention to how this geometry evolves over time, how the cosmic shape changes as the universe ages. The universe we observe today is vastly different from its earlier incarnations. In its infancy, it was a hot, dense plasma, opaque to light and rapidly expanding. Today, it is cool, diffuse, and transparent, filled with galaxies that continue to move apart as space itself stretches. But what of its shape? Has the fundamental geometry of the cosmos remained constant through this evolution, or has it too undergone profound transformations? To answer this question, we must begin at the beginning, or at least as close to the beginning as our physics can reliably take us. The earliest epoch we can confidently describe is cosmic inflation, a period of extraordinarily rapid expansion, thought to have occurred during the first tiny fraction of a second after the Big Bang. During inflation, the universe expanded by a factor of at least 10 raised to the power of 26 in just 10 to the negative 34 seconds. This explosive growth stretched space so dramatically that any initial curvature would have been flattened out, much like how the surface of a balloon approaches flatness as it inflates to enormous size. This inflationary episode explains one of the great puzzles in cosmology, why the universe appears so flat today. Without inflation, the density of the universe would need to have been extraordinarily close to the critical value in its early stages, fine-tuned to an incredible degree of precision. Even tiny deviations from flatness would have been amplified over billions of years of cosmic evolution, leading to a universe that is either strongly curved or that would have recollapsed long ago. Inflation resolves this flatness problem by proposing that the universe was flattened by its early exponential expansion, regardless of its initial geometry. Our observable universe, in this picture, is just a tiny patch of a much larger cosmos, a patch that appears flat for the same reason that a small section of the Earth's surface appears flat to us, despite the planet's overall curvature. But inflation did more than just flatten the cosmos. It also seeded the universe with quantum fluctuations, tiny variations in density that would later grow into the cosmic web of galaxies, clusters, and voids we observe today. These density fluctuations, stretched from microscopic to astronomical scales by inflationary expansion, left their imprint on the cosmic microwave background radiation, creating the pattern of temperature variations we observe in this relic light from the early universe. After inflation ended, the universe entered an era dominated by radiation, a hot plasma of photons and elementary particles. During this phase, the universe continued to expand, but at a much slower rate than during inflation. The geometry of space during this period was largely determined by the ratio of the actual density of the universe to the critical density needed for a flat geometry. If this ratio, which cosmologists denote by the symbol omega, was exactly 1, then space remained flat as it expanded. If omega exceeded 1, then space had positive curvature, like a sphere, and this curvature would have become more pronounced as the universe expanded. If omega was less than 1, space had negative curvature, like a saddle, which would similarly have become more extreme with time. This relationship between density and curvature stems from Einstein's theory of general relativity, which describes how matter and energy curve space-time. In a universe filled with normal matter and radiation, a higher density means stronger gravity, which curves space more sharply. The critical density represents the exact amount of matter and energy needed to balance the universe between eternal expansion and eventual recollapse, corresponding to a flat geometry. As the universe continued to expand and cool, it eventually reached a temperature low enough for electrons to combine with nuclei, forming neutral atoms. This event, known as recombination, occurred about 380,000 years after the Big Bang. At this point, the universe became transparent to light, and the cosmic microwave background radiation was released to travel freely through space. The geometry of the universe at the time of recombination is encoded in the cosmic microwave background. By measuring the angular size of temperature fluctuations in this ancient light, cosmologists can infer the curvature of the space through which it has traveled. These measurements indicate that the universe was remarkably close to flat at this early epoch, consistent with the predictions of cosmic inflation. Following recombination, the universe entered a matter-dominated era. The density of radiation, which decreases more rapidly than matter as the universe expands, became subdominant to the density of matter, both visible and dark. During this period, the expansion of the universe gradually slowed due to the gravitational attraction of matter, but it never stopped completely. In a matter-dominated universe with no dark energy, the evolution of geometry would follow a simple pattern. If the universe began exactly flat, it would remain flat as it expanded, with parallel lines staying parallel forever. If it began with positive curvature, this curvature would become more pronounced over time, eventually leading to a recollapse. If it began with negative curvature, it would become increasingly hyperbolic as it expanded eternally. But about 5 billion years ago, something remarkable happened. The ever-diluting density of matter fell below the roughly constant density of dark energy, and the universe entered a new phase in its evolution. The repulsive effect of dark energy began to dominate over the attractive force of gravity, causing the expansion of the universe to accelerate rather than decelerate. This transition to dark energy domination profoundly affected the evolution of cosmic geometry. In a universe dominated by a cosmological constant, the simplest form of dark energy, the expansion accelerates exponentially. This has the effect of gradually flattening space, regardless of its initial curvature. If the universe has positive curvature, like a sphere, dark energy works against this curvature, stretching space and making it appear flatter over time from our perspective. If the universe has negative curvature, like a saddle, dark energy similarly stretches this curvature, making it less extreme. And if the universe is already flat, dark energy preserves this flatness as the cosmos expands. This flattening effect can be understood intuitively by considering the horizon problem. As the universe expands exponentially under the influence of dark energy, regions of space that were once in causal contact move beyond each other's cosmic horizons. They become unable to influence each other gravitationally or communicate in any way. This effectively isolates different regions of the universe from one another, each expanding as if it were its own separate cosmos. From the perspective of observers in any one of these regions, like ourselves, the observable universe appears increasingly flat as it expands. Even if the global geometry of the entire cosmos beyond our horizon has a different curvature, this is analogous to how a small patch of a curved surface appears increasingly flat as it is stretched. Current observations suggest that our universe is flat within the limits of measurement, with any curvature being less than about 0.5%. But given the flattening effect of dark energy, this does not necessarily mean that the universe is exactly flat on scales larger than we can observe, or that it has always been flat throughout its history. Let us now consider how the evolution of cosmic geometry influences the distribution of matter and the formation of structure in the universe. In the early, radiation-dominated era, the growth of density fluctuations was suppressed. But once matter came to dominate, these fluctuations began to grow through gravitational instability, with regions of slightly higher density attracting more matter and becoming denser still. The geometry of space influenced this process of structure formation. In a flat universe, structure grows at a rate determined by the balance between gravitational attraction and cosmic expansion. In a positively curved universe, structure would form more quickly, as the additional gravity from the higher overall density would enhance the growth of fluctuations. In a negatively curved universe, structure would form more slowly, as the lower density would provide less gravitational reinforcement. Once dark energy began to dominate, the accelerating expansion started to suppress the formation of larger structures. Regions of space that had not yet collapsed under their own gravity were pulled apart by the accelerating expansion, preventing them from forming bound structures. This effectively sets a maximum size scale for gravitationally bound objects in our universe. The interplay between cosmic geometry and structure formation creates a fascinating feedback loop. The distribution of matter determines the curvature of space through Einstein's field equations. This curvature, in turn, influences how matter moves and clumps together, which further alters the curvature. The shape of space and the distribution of matter evolve together, each responding to changes in the other. On the largest scales, where the universe can be treated as homogeneous and isotropic, this co-evolution is described by the Friedmann equations, which relate the expansion rate of the universe to its energy content and curvature. But on smaller scales, where the distribution of matter becomes lumpy and complex, the relationship between geometry and structure becomes much more intricate. Around massive objects like stars, black holes, and galaxies, space curves sharply, creating regions of strong gravitational influence. These local distortions in space-time affect the motion of nearby objects and the paths of light rays, creating phenomena like gravitational lensing and gravitational time dilation. As these massive objects move through the cosmos, they carry their gravitational distortions with them, creating ripples in space-time known as gravitational waves. When particularly violent events occur, such as the collision of two black holes or neutron stars, these ripples can become quite strong, propagating through the universe at the speed of light. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves from a pair of merging black holes. This momentous discovery not only confirmed a key prediction of Einstein's theory, but also provided a new way to probe the geometry of space-time itself. By measuring how gravitational waves propagate through the cosmos, scientists can test whether space behaves as Einstein's theory predicts, potentially revealing new insights into cosmic geometry and its evolution. The evolution of cosmic geometry also has profound implications for the ultimate fate of the universe. In the standard cosmological model, with a flat universe dominated by a cosmological constant, the expansion will continue to accelerate forever. Galaxies beyond our local group will recede faster and faster, eventually disappearing from view as their light becomes too redshifted to detect. The observable universe will grow increasingly empty, with fewer and fewer galaxies remaining within our cosmic horizon. But this picture could change if the properties of dark energy evolve over time. If dark energy weakens or changes its nature, the acceleration could eventually halt or even reverse. Alternatively, if dark energy grows stronger with time, it could potentially lead to a big rip, tearing apart bound structures from galaxies down to atoms. The evolution of cosmic geometry is thus intimately tied to questions of cosmic eschatology, the study of the ultimate fate of the universe. Will the cosmos expand forever, growing ever colder and more diffuse? Will it eventually recollapse in a big crunch? Or will it meet some other, perhaps even stranger fate? The answer depends on the nature of dark energy and the resulting evolution of cosmic geometry. Beyond these physical considerations, the changing shape of the universe raises profound philosophical questions. If the geometry of reality itself evolves over time, what does this tell us about the nature of space, time, and existence? Is the universe a fixed, eternal structure, or a dynamic, ever-changing entity? And what role do conscious observers like ourselves play in this cosmic evolution? Some interpretations of quantum mechanics suggest that observation itself plays a role in determining physical reality. In the quantum realm, particles exist in superpositions of states until measured, at which point they collapse into definite states. Applied to cosmology, this raises the intriguing possibility that the universe's geometry might be influenced by the very act of observing it. While such speculations venture beyond mainstream cosmology, they remind us that our understanding of cosmic geometry remains incomplete. We have made remarkable progress in measuring and modeling the shape of the universe, but many mysteries remain. The nature of dark energy, the global topology of space, the ultimate fate of the cosmos. These questions continue to push the boundaries of human knowledge. What we can say with confidence is that the universe is not static. It evolves and changes, its geometry responding to the matter and energy within it. The shape of space is not fixed, but dynamic, growing and flowing as the cosmos expands and ages. This realization, that even the stage upon which cosmic drama unfolds is itself changing, represents one of the great insights of modern cosmology. As we lie here, contemplating these vast cosmic rhythms, we might reflect on our own brief place within them. We exist at a particular moment in the universe's geometric evolution, a time when dark energy has just begun to dominate, when the cosmic expansion has started to accelerate. Had we evolved billions of years earlier or later, we would have witnessed a cosmos with different properties, a different geometric evolution. In this sense, the changing shape of the universe forms part of the backdrop to our existence, part of the cosmic context in which life and consciousness have emerged. We are not just observers of cosmic geometry, but participants in its unfolding story, matter that has become aware of the shape of the space it inhabits, and of how that shape changes with time. This awareness, this capacity to measure and model the changing geometry of reality, represents something remarkable in the cosmic scheme. Through science and mathematics, through observation and theory, we have begun to comprehend the shape of everything and how it evolves. In doing so, we participate in the universe's ongoing process of self-discovery, as matter organized into conscious beings seeks to understand the geometric stage on which it exists. As we drift towards sleep, let us carry this awareness with us, this recognition that we inhabit a dynamically evolving geometry, a cosmos whose very shape changes as it expands and ages. In our next chapter, we will explore even more exotic possibilities, venturing into the realm of multiple universes with different geometries. But for now, let us rest in the knowledge that even the fabric of space itself is not static, but flowing, growing, evolving through the eons, carrying us along in its majestic unfolding. Our universe may be one among many, each with its own form. Throughout our journey, we have explored the shape of our observable universe, how we measure it, and how it evolves over cosmic time. But now we venture into more speculative terrain, considering the possibility that our universe might be just one region in a much larger multiverse, a vast ensemble of universes, each with its own distinct geometry. The concept of a multiverse represents one of the most profound shifts in our cosmic perspective since the Copernican revolution. Just as Copernicus dethroned Earth from the center of the cosmos, multiverse theories suggest that our entire observable universe may be just one bubble in an immensely larger and more diverse reality. Several lines of theoretical inquiry have converged on this remarkable possibility. The first emerges from cosmic inflation, the theory that our universe underwent a period of exponential expansion in its earliest moments. While inflation elegantly explains many observed features of our cosmos, including its flatness and the pattern of temperature fluctuations in the cosmic microwave background, the theory may have consequences beyond our observable horizon. Many versions of inflationary theory suggest that inflation does not end everywhere at once. Instead, as some regions stop inflating and begin to evolve into universes like our own, inflation continues in other regions, expanding them far beyond our cosmic horizon. This process, known as eternal inflation, would generate an infinite number of bubble universes, each emerging from its own exit from the inflationary state. In this scenario, our observable universe is just one bubble in a vast cosmic foam, one region where inflation happened to end and allow matter and radiation as we know them to form. Beyond our cosmic horizon, other bubble universes continue to form, each with potentially different physical conditions, different geometries, and even different physical laws. These bubble universes might have very different geometric properties from our own. Some might be flat, others positively curved like cosmic spheres, and others negatively curved like cosmic saddles. Some might continue expanding forever, while others might eventually recollapse. The geometric diversity of this inflationary multiverse could be vast, encompassing all possible spatial curvatures and evolutionary trajectories. A second path to the multiverse comes from string theory, our most ambitious attempt to unify all the forces of nature, including gravity, into a single theoretical framework. String theory suggests that the fundamental building blocks of reality are not point-like particles, but tiny, vibrating strings, whose different modes of vibration manifest as different particles and forces. For string theory to be mathematically consistent, it requires extra dimensions beyond the three spatial dimensions and one time dimension we directly experience. These extra dimensions are thought to be compactified, curled up so tightly that they are effectively invisible to us, yet they shape the physics we observe in our four-dimensional world. The remarkable discovery that emerged in the early 21st century is that string theory seems to allow an enormous number of different ways to compactify these extra dimensions. perhaps as many as 10 raised to the power of 500 distinct configurations. Each of these configurations would give rise to a universe with different physical laws, different constants of nature, and different geometric properties. This vast landscape of possible string theory solutions suggests that perhaps all of these different configurations are actually realized somewhere in a vast multiverse. Our universe, with its particular physical laws and geometric properties, would be just one valley in an immense landscape of possibilities, one solution among many to the underlying equations of string theory. In this string theory landscape, different regions of the multiverse could have wildly different geometries. Some might have spatial dimensions that expand, while others contract. Some might experience periods of accelerated expansion, similar to our own dark energy-driven acceleration, while others might never enter such a phase. The geometric diversity would be even greater than in the inflationary multiverse scenario. A third approach to the multiverse comes from quantum mechanics, specifically from the many worlds interpretation proposed by Hugh Everett in the 1950s. This interpretation suggests that quantum mechanics does not collapse wave functions when measurements occur, but instead branches reality into multiple worlds, each representing a different measurement outcome. In the quantum multiverse, reality would consist of an ever-branching tree of universes, diverging with every quantum event. While most versions of the many worlds interpretation focus on the branching of events within the same physical laws and geometric framework, some theorists have explored whether quantum processes might also create branches with different physical laws, or cosmic geometries. These different pathways to the multiverse are not mutually exclusive. They might represent different aspects or levels of the same underlying multiversal reality. Together, they suggest a picture of reality far grander and more diverse than our observable universe alone, a vast tapestry of different universes with varying geometries, physical laws, and evolutionary trajectories. But this raises a profound question. If other universes exist beyond our cosmic horizon, with different geometric properties, how could we ever detect them or test their existence? Are multiverse theories genuinely scientific if they make predictions about realms that seem forever beyond our observational reach? Cosmologists have explored several possible ways to detect signatures of a multiverse, though all remain speculative. One possibility involves cosmic bubble collisions. If our universe is one bubble among many in an inflating multiverse, it might occasionally collide with other bubbles. Such collisions could leave detectable imprints on the cosmic microwave background, circular patterns of temperature variation that would stand out from the standard fluctuations predicted by inflation. Another possibility involves quantum entanglement between our universe and others. Some theoretical physicists have suggested that quantum mechanics might allow for subtle correlations between different universes, potentially leaving observable signatures in the precise pattern of cosmic structure in our own universe. A third approach focuses on the statistical predictions of multiverse theories. While we cannot observe other universes directly, we can ask whether the properties of our own universe are what we would expect if it were randomly selected from a vast ensemble with different properties. This anthropic reasoning suggests that we should not be surprised to find ourselves in a universe with properties that allow for our existence, even if such universes are rare in the multiverse as a whole. These approaches remain highly speculative, and many physicists remain skeptical about whether multiverse theories can ever be empirically tested. Yet the mathematical consistency and theoretical appeal of these frameworks continue to drive interest in the possibility that our universe might be one geometric form among many in a vast multiversal reality. Let us explore in more detail what variable geometry might mean across a multiverse. In our observable universe, we have measured space to be remarkably flat, with any curvature being less than about 0.5%. But other universes in a multiverse might have much stronger spatial curvature, either positive or negative. A universe with strong positive curvature would be finite in size, like the surface of a hypersphere. Light traveling through such a universe would eventually return to its starting point, having circumnavigated the entire cosmos. Such a universe might appear to its inhabitants as if it contained multiple copies of the same objects, as light from distant galaxies would reach observers from different directions after traveling different paths around the curved cosmos. A universe with strong negative curvature would have a hyperbolic geometry, expanding much more rapidly at large distances than a flat universe. In such a cosmos, the volume of space would increase exponentially with distance from any point, allowing for potentially much more complex structures than our own universe can support. Different universes might also have different numbers of large spatial dimensions. While our universe has 3 large spatial dimensions, string theory allows for the possibility of universes with different numbers of expanded dimensions. A 2-dimensional universe would be like a vast sheet, while a 4-dimensional universe would have an extra direction perpendicular to our familiar 3. The number of dimensions dramatically affects the behavior of physical systems. In a 2-dimensional universe, there would be no stable atomic orbits, making complex chemistry and life as we know it impossible. In a 4-dimensional universe, planetary orbits would be unstable, and atoms might not form at all. Our 3-dimensional cosmos seems finely tuned to allow for the complexity we observe. Even more exotic is the possibility of universes with different numbers of time dimensions. Our universe has 1 time dimension, creating a clear arrow of time from past to future. But some theoretical frameworks allow for universes with multiple time dimensions, where the concept of causality and temporal evolution would be radically different from our own experience. The overall topology of different universes might also vary. Even universes with the same local geometry can have different global topologies, like a flat sheet versus a flat torus, where opposite edges connect. Some universes might have bizarre topological features like handles or crosscaps, creating pathways through space that would seem magical from our perspective. Another variable across the multiverse might be the dimensionality of elementary particles themselves. In our universe, fundamental particles appear to be 0-dimensional points, while string theory suggests they are actually 1-dimensional objects. But other universes might contain fundamental objects with different dimensionality, from 0-dimensional points to 2-dimensional membranes or higher dimensional branes. The geometry of a universe is intimately connected to its physical laws. Different geometries enable or constrain different types of physical interactions, different forms of symmetry, and different possibilities for complexity. The vast geometric diversity of a potential multiverse would thus imply an equally vast diversity of physical behaviors and phenomena. This geometric diversity raises profound questions about the nature of physical law itself. In our universe, we observe consistent physical laws that can be described by elegant mathematical equations. But are these laws unique and necessary, or are they just one possibility among many? In a multiverse with variable geometry, physical laws might themselves be emergent properties, dependent on the particular geometric configuration of each universe. The concept of a multiverse with variable geometry also has implications for how we understand the apparent fine-tuning of our own universe. Our cosmos seems remarkably well calibrated for complexity and life, with physical constants and laws that precisely allow for stable atoms, stars, and galaxies. If slight changes were made to these constants, the universe would be sterile, unable to form the complex structures needed for life. In a single universe scenario, this fine-tuning is difficult to explain, but in a multiverse with variable geometry and physics, it becomes less surprising. If different regions have different physical properties, then naturally we find ourselves in one of the rare regions where the conditions allow for our existence. This anthropic reasoning does not explain why the multiverse exists, but it does help explain why we observe the particular cosmic geometry and physical laws that we do. The possibility of a multiverse with variable geometry also changes how we might think about the ultimate fate of intelligent life. In a single universe scenario, the accelerating expansion driven by dark energy seems to doom all life to an eventually cold, diffuse, and isolated fate. But if travel or communication between universes were somehow possible, even in principle, it would open up vastly greater possibilities for the long-term future of intelligence. Some speculative physics suggest that advanced civilizations might eventually learn to create baby universes, new cosmological regions with their own space and time, potentially with chosen geometric properties. These baby universes might even allow for a form of cosmic reproduction, where the physical laws and geometric properties that allow for complexity and life are passed on to new cosmic regions. Such speculations take us far beyond established science, but they illustrate how the concept of a multiverse with variable geometry expands not just our understanding of what reality might be, but also the potential long-term horizons for intelligent life within that reality. As we contemplate these vast possibilities, it is worth noting that the concept of a multiverse is not entirely new. Many ancient mythologies and philosophical traditions conceived of multiple worlds or realms beyond our own. The Greek philosopher Democritus speculated about an infinite number of worlds, while Hindu cosmology envisions countless universes in an eternal cycle of creation and destruction. What is new is our ability to formulate these possibilities in the precise language of mathematics and physics, to connect them to our best theories of how our own universe works, and to begin exploring how they might be tested through observation and experiment. The multiverse has moved from pure speculation to a serious, if still controversial, scientific hypothesis. Whether or not a multiverse with variable geometry actually exists, the concept itself represents a remarkable expansion of our cosmic perspective. Just as Copernicus showed that Earth is not the center of the cosmos, and Edwin Hubble showed that our galaxy is just one among billions, multiverse theories suggest that our entire observable universe might be just one region in a far vaster and more diverse reality. This humbling yet awe-inspiring possibility reminds us of the scope of what remains unknown, the depth of reality that might lie beyond our current understanding. It suggests that the cosmos might be far stranger, more diverse, and more geometrically rich than we have imagined. A tapestry of universes, each with its own shape and structure, its own physical laws and evolutionary trajectory. As we drift towards sleep, let us hold this expanded perspective in mind, this possibility that our universe, with its particular geometry and physical laws, might be just one form among many in a vast multiversal reality. In our next chapter, we will bring our focus back to our own universe, exploring how its shape might influence the emergence of life and consciousness within it. But for now, let us rest in the vastness of possibility, in the geometric diversity that might exist beyond our cosmic horizon. Shape and life are entwined in cosmic harmony. Throughout our exploration of cosmic geometry, we have treated the shape of the universe primarily as a mathematical and observational question, something to be measured and modeled through astronomical observations and physical theories. But now we turn to a more profound question. How might the fundamental geometry of the cosmos influence the emergence of life and consciousness within it? How does shape affect the possibility of our own existence? This question connects cosmology to what philosophers call the anthropic principle, the observation that the universe appears remarkably well suited for the emergence of life. Many physical constants and cosmic parameters seem finely tuned to allow for stable atoms, stars, planets, and ultimately complex beings like ourselves. Is the shape of the universe similarly tuned? And if so, why? Let us begin by considering how different cosmic geometries might influence the basic building blocks of matter. The stability of atoms depends on the precise balance of forces within them, particularly the electromagnetic force that binds electrons to nuclei, and the strong nuclear force that holds protons and neutrons together in nuclei. These forces, in turn, propagate through space according to its underlying geometry. In a flat universe like our own, these forces follow an inverse square law, diminishing with the square of the distance. This relationship is not arbitrary but emerges from the three-dimensional nature of our space. In a universe with a different number of large spatial dimensions, forces would follow different distance relationships, potentially destabilizing atoms as we know them. For instance, in a universe with 4 large spatial dimensions, gravitational and electromagnetic forces would follow an inverse cube law. Stable planetary orbits would not exist, and electrons would either spiral into nuclei or escape from them entirely. The chemistry that underlies life as we know it would be impossible. Similarly, in a 2-dimensional universe, forces would follow a simple inverse distance law rather than an inverse square law. Atoms in such a universe would behave very differently, and complex chemistry would likely be impossible. The three-dimensionality of our space thus appears crucial for the stable structures that make life possible. But dimensionality is just one aspect of geometry. What about curvature? Would life be possible in a strongly curved universe? The answer is complex and depends on the scale of the curvature relative to the scales of biological processes. If the radius of curvature of the universe is much larger than the typical scales of life, then curved space would not directly prevent life from emerging. Locally, space would appear nearly flat, and biological processes could proceed much as they do in our nearly flat cosmos. However, if the curvature were strong enough to be significant at biological scales, it could disrupt the chemistry and physics upon which life depends. In a universe with strong positive curvature, like a hypersphere with a relatively small radius, light rays would converge rather than remaining parallel or diverging. This would create optical effects unlike anything in our experience. Visual perception, which many forms of life on Earth rely upon, would work very differently. Evolution would need to find different solutions for gathering information about the environment. A universe with strong negative curvature would present different challenges. Space would expand more rapidly with distance, potentially limiting the development of large-scale cosmic structures like galaxy clusters that might be important for creating the heavy elements life requires. The distribution of matter in such a universe might be too diffuse to allow for the rich chemistry needed for biological complexity. The global topology of space might also influence the possibility of life. In a universe with a non-trivial topology, like a three-dimensional torus, light could travel around the entire cosmos and return to its starting point from the opposite direction. This could create multiple images of the same objects as seen from different directions, potentially confusing visual perception systems that evolved in such an environment. But perhaps the most significant way that cosmic geometry influences life is through its effect on the overall evolution of the universe. As we have seen in previous chapters, the shape of the universe helps determine its ultimate fate, whether it will expand forever, recollapse, or reach some other end state. This cosmic fate, in turn, constrains how long complex structures like galaxies, stars, planets, and living beings can exist. In a closed universe with positive curvature and no dark energy, the cosmos would eventually stop expanding and begin to contract, leading to a big crunch where all matter and energy are compressed into an incredibly hot, dense state. Such a universe would have a finite lifetime, limiting how long life could exist and evolve. In an open universe with negative curvature, or a flat universe like our own, both dominated by dark energy, the expansion continues forever, with galaxies moving apart at an ever-increasing rate. While this allows for a potentially infinite future, it eventually creates isolated island universes, galaxy groups that lose causal contact with the rest of the cosmos, as space expands too rapidly for light to traverse the growing gaps. Our own universe appears to be transitioning to this latter state, with the acceleration driven by dark energy gradually isolating our local group of galaxies from the rest of the cosmos. In the far future, galaxies beyond our local cluster will recede beyond our cosmic horizon, becoming forever unobservable. This geometry constrains the long-term future of any civilizations that might emerge in our universe, limiting their access to matter and energy beyond their local galactic environment. These cosmic constraints have led some philosophers and cosmologists to consider whether advanced civilizations might somehow modify the geometry of their universe to escape these limitations. While such speculations go far beyond current physics, they illustrate how intimately the shape of the cosmos is connected to the ultimate horizons of life and intelligence within it. Beyond these physical considerations, the geometry of the universe might also influence how intelligent beings conceptualize reality itself. Our human mathematical and physical intuitions have been shaped by evolution in a three-dimensional, nearly flat space. We find certain geometric concepts intuitive and others deeply counterintuitive. For instance, most humans find it difficult to truly visualize 4 or more spatial dimensions, or to intuitively grasp how parallel lines might converge in curved space. Our brains have evolved to navigate and understand a specifically shaped reality, and this shapes our concepts and theories in turn. Intelligent beings evolving in a universe with different geometric properties might develop very different intuitions and conceptual frameworks. Their mathematics, physics, and philosophy might take forms we would find alien or incomprehensible, just as our own might seem to them. The shape of their cosmos would shape their minds, just as ours has shaped our own. This connection between cosmic geometry and cognition raises profound questions about the relationship between mind and reality. Is mathematics invented by minds to describe reality, or is it discovered as an inherent feature of reality itself? The fact that geometric concepts seem applicable across vastly different scales, from quantum particles to the cosmos as a whole, suggests some deep connection between the structure of reality and the structure of thought. The ancient Greeks believed in a fundamental harmony between the human mind and the cosmos, a correspondence that made mathematical understanding possible. Modern physics has revealed a reality far stranger than they imagined, with quantum uncertainty, curved space-time, and potentially a multiverse of different geometries. Yet somehow, the human mind has proven capable of formulating mathematical models that capture these strange features, suggesting some deep resonance between mind and world. Perhaps this resonance is itself a product of evolution. Minds that could accurately model reality, that could develop concepts and intuitions matching the actual structure of the world, would have a survival advantage over those that could not. Our geometric intuitions might thus reflect the shape of the reality in which our ancestors evolved. If this is true, then the shape of the universe has influenced not just our physical existence, but our consciousness itself, our ways of thinking and understanding. We are not just in the universe. The universe, with its particular geometry, is in us, shaping our thoughts and perceptions from within. This perspective invites us to consider the fine-tuning of cosmic geometry in a new light. Perhaps the universe's shape is hospitable to life not by chance or necessity, but through a more subtle relationship where consciousness and reality co-evolve. Some philosophers have proposed that the cosmos as a whole might possess a kind of proto-consciousness, a view known as panpsychism, while others suggest that consciousness might somehow be fundamental to reality rather than emerging from it. While such philosophical speculations go beyond established science, they illustrate how questions about cosmic geometry ultimately connect to the deepest questions about consciousness, existence, and meaning. The shape of the universe is not merely a physical fact, but a context within which the drama of life and mind unfolds. Let us consider more concretely how the stability of matter depends on cosmic geometry. The forces that hold atoms together and the quantum mechanical rules that govern electron orbits are intimately connected to the dimensionality and structure of space. The Pauli exclusion principle, which prevents electrons from occupying the same quantum state and thus enables the complex electron shell structure of atoms, depends on how fermions behave in three-dimensional space. In a universe with different geometric properties, the basic behaviors of particles could be altered, potentially making complex chemistry impossible. If electrons did not form stable shells, or if the nuclear forces had different strengths or ranges due to geometrical effects, the periodic table of elements might look entirely different, or might not exist at all. The fundamental forces themselves seem fine-tuned for complexity. If gravity was slightly stronger relative to the electromagnetic force, stars would burn out more quickly, perhaps not living long enough to support the evolution of complex life on planets. If the strong nuclear force was slightly weaker, complex nuclei could not form, eliminating most of the periodic table. These delicate balances depend in part on how these forces propagate through space, which in turn depends on its geometry. Even the homogeneity and isotropy of our universe, the fact that it looks roughly the same in all places and directions on large scales, seems important for life. This large-scale uniformity, which general relativity connects to the overall geometry of the cosmos, allows for the formation of galaxies and stars distributed throughout space, rather than being concentrated in one region. It provides a vast arena in which the processes leading to life can occur in many locations, increasing the probability of life emerging somewhere. The age of the universe also matters for life, and this too connects to cosmic geometry. A universe that expanded too quickly might never form galaxies at all. One that expanded too slowly might recollapse before life had time to evolve. Our universe's expansion history, determined in part by its geometry, has allowed it to exist for about 14 billion years, enough time for stars to forge heavy elements, for planets to form, and for complex life to evolve, at least on Earth. The relationship between cosmic shape and time is particularly intriguing. Einstein's theory of relativity unifies space and time into a single entity, space-time, whose geometry determines how matter and energy move and interact. The arrow of time itself, the fact that we experience time as flowing from past to future, may be connected to the overall geometry and expansion of the cosmos. In a universe that was static or collapsing rather than expanding, the thermodynamic arrow of time might not align with the cosmological arrow. This could create conditions where ordered structures become less likely to form and persist, potentially making life impossible. The fact that our universe has been expanding throughout its history creates a consistent direction for processes like the cooling of hot objects, the diffusion of gases, and the evolution of complex structures from simpler ones. Some physicists have even speculated that life itself might be connected to the increase of entropy, the gradual dispersal of energy into more disorganized forms. Life forms create and maintain internal order by exporting entropy to their surroundings, a process that works because of the thermodynamic arrow of time established by cosmic expansion. In this view, life is not just influenced by cosmic geometry, but is a process intimately connected to the expanding, evolving shape of space-time itself. As we reflect on these deep connections between cosmic shape and the possibility of life, we are reminded of the remarkable position we occupy in the universe. We exist in a cosmos that appears, for reasons we do not fully understand, to have just the right geometric and physical properties to allow for our emergence. We inhabit a universe whose shape permits the existence of minds capable of contemplating that shape. This realization inspires both humility and wonder. Humility, because we recognize how contingent our existence is on the specific properties of the cosmos, how different the universe might have been, and how easily it might have taken forms hostile to life. Wonder, because against all odds, the universe does have a shape that allows for us, for consciousness, for the cosmos to become aware of itself through beings like ourselves. Perhaps this is the most profound implication of our exploration of cosmic geometry. The universe has a shape that enables it to be known. Through the emergence of life and mind, the cosmos has evolved the capacity to measure and model its own form, to chart its own evolution, to contemplate its own existence. We are the means by which the universe comes to know itself, the point where cosmic geometry curves back upon itself in the form of conscious thought. As we drift towards sleep, let us carry this awareness with us, this recognition of the deep connection between the shape of everything and our own existence. In our next chapter, we will explore the observational challenges that limit our knowledge of cosmic geometry, the practical and theoretical boundaries of what we can know about the shape of reality. But for now, let us rest in appreciation of this remarkable harmony between the form of the cosmos and the emergence of life within it. The universe keeps its secrets well guarded. As we have journeyed through cosmic geometry, we have encountered a remarkable convergence of theory and observation. Mathematical models of curved space-time, developed primarily by Einstein and his successors, have been confirmed by increasingly precise astronomical measurements. We have mapped the cosmic microwave background, charted the distribution of galaxies across billions of light years, and detected the subtle effects of dark energy on cosmic expansion. Yet despite these triumphs, fundamental limitations constrain our ability to fully determine the shape of the cosmos. These observational challenges are not merely technical problems to be solved with better instruments, though improved technology certainly helps. Rather, they reflect deeper constraints, some practical, some theoretical, and some perhaps fundamental to the nature of observation itself. In this chapter, we explore these challenges and consider what they tell us about the limits of cosmic knowledge. The most basic limitation we face is the finite speed of light. Light travels at approximately 300,000 kilometers per second, an enormous speed by human standards, but finite nonetheless. This means that when we look at distant objects, we see them not as they are now, but as they were when the light began its journey toward us. The farther we look, the further back in time we see. This light travel time creates what astronomers call the observable universe, the spherical region from which light has had time to reach us since the beginning of the cosmos. The radius of this observable sphere is about 46 billion light-years, significantly larger than the 13.8 billion years age of the universe, because space itself has been expanding as light travels through it. Beyond this cosmic horizon lies space we cannot observe, not because of any limitation in our instruments, but because light from those regions has not yet had time to reach us. The universe may extend far beyond what we can see, perhaps infinitely, with geometric properties potentially different from those within our observable patch. This cosmic horizon is not fixed, but expands at the speed of light, gradually bringing more distant regions into view. However, the accelerating expansion of the universe, driven by dark energy, works against this process. Regions of space that are currently just beyond our horizon will, in many cases, never become observable, as they recede faster than light can traverse the growing gap. Our observable universe thus represents a limited and eventually shrinking sample of the whole cosmos. Within this observable sphere, additional challenges arise from the uneven distribution of matter. The universe contains structures at all scales, from planets and stars to galaxies, clusters, and vast cosmic filaments and voids. These inhomogeneities distort space-time locally, creating departures from the smooth, uniform geometry assumed in our simplest cosmological models. General relativity tells us that mass curves space-time, creating what we experience as gravity. Every object, from a grain of sand to a supermassive black hole, contributes to this curvature. The combined effect of all these gravitational influences creates a complex, dynamic geometry that can only be approximated by our idealized models of cosmic shape. When we measure the curvature of the universe, we are essentially averaging over these local variations to determine the overall, large-scale geometry. But this averaging process introduces uncertainties and potential biases. Different methods of averaging can lead to slightly different results, and the regions we can observe might not be fully representative of the universe as a whole. This variability leads to what cosmologists call cosmic variance, the statistical uncertainty that arises from observing a limited sample of the universe. Even with perfect instruments, cosmic variance would limit our ability to determine the universe's shape precisely. It is like trying to determine the curvature of the Earth from measurements taken in a single city, when local hills and valleys create deviations from the planet's overall spherical form. Another significant challenge comes from the evolution of the universe itself. The cosmos is not static but dynamic, its geometry changing as it expands and evolves. The shape we measure today is not the same as it was billions of years ago, nor the same as it will be billions of years in the future. This evolution means that different observational techniques, looking at phenomena from different cosmic epochs, might yield slightly different measurements of curvature. The cosmic microwave background shows us the geometry of the universe when it was just 380,000 years old. Surveys of galaxy distributions reveal the shape when the universe was several billion years old. Measurements of the current expansion rate reflect the geometry of the more recent universe. Combining these observations into a coherent picture of how cosmic geometry has evolved requires sophisticated statistical techniques and theoretical models. Small discrepancies between measurements from different epochs could either indicate errors in our observations, limitations in our theories, or genuine evolution in the universe's shape. Perhaps the most intriguing challenge comes from the global topology of the universe. As we have discussed in earlier chapters, the local curvature of space does not fully determine its global connectivity. A flat universe could still have a non-trivial topology, connecting back on itself in complex ways, like a three-dimensional analog of a torus. Detecting such topological features would require identifying matching patterns on opposite sides of the sky, as if we were seeing the same structures from different directions. But the finite age of the universe limits how far we can see, and thus how large a topological repeat distance we could detect. If the universe does wrap around itself, but on a scale larger than our observable horizon, we might never be able to detect this directly. These observational challenges are compounded by the subtle and elusive nature of the phenomena we seek to measure. The curvature of the universe, if it exists at all, is extremely small, less than 0.5%, according to our best current measurements. Detecting such slight curvature requires extraordinary precision beyond what most of our current instruments can achieve. This precision is limited by various sources of uncertainty. Random statistical fluctuations in our measurements introduce noise that can mask the signals of cosmic curvature. Systematic errors, arising from imperfections in our instruments or assumptions in our analysis methods, can bias our results in ways that are difficult to fully account for. For instance, when measuring the cosmic microwave background, astronomers must carefully subtract foreground emissions from our own galaxy and other sources. Any errors in this subtraction process could affect the measured sizes of temperature fluctuations, which in turn influence our estimates of cosmic curvature. Similarly, when using distant supernovae to track cosmic expansion, astronomers must account for how these stellar explosions evolve over time and how interstellar dust might dim their light. Small errors in these corrections could lead to incorrect inferences about the geometry and expansion history of the universe. Even our most basic cosmic measurements face challenges. The Hubble constant, which determines the current expansion rate of the universe, has been measured using different methods that yield slightly different results. This Hubble tension, as astronomers call it, could potentially indicate systematic errors in our measurements, limitations in our theoretical models, or perhaps even new physics beyond the standard cosmological framework. Let us consider more specifically how these challenges affect our attempts to measure the three main geometric possibilities for our universe: flat, closed, or open. The flat case, where parallel lines remain parallel forever, and the sum of angles in a triangle equals exactly 180 degrees, represents a knife edge between the closed and open alternatives. Current observations suggest that our universe is remarkably close to flat, but determining whether it is exactly flat or just very nearly so remains extremely difficult. If the universe is closed, with positive curvature like a higher dimensional sphere, we would expect to see slightly larger than predicted angular sizes for distant objects, particularly the fluctuations in the cosmic microwave background. But the effect is subtle and easily masked by other factors that can affect apparent sizes, such as gravitational lensing by intervening matter. Similarly, if the universe is open, with negative curvature like a saddle shape, distant objects would appear slightly smaller than expected. Again, this effect is difficult to disentangle from other phenomena that can affect apparent sizes. The current consensus among cosmologists, based on multiple lines of evidence, is that any deviation from flatness must be very small, less than 0.5%. But determining the exact degree of curvature, and whether it is precisely zero or just very close to zero, remains a significant challenge. Another intriguing possibility is that the curvature of the universe might vary across regions far larger than we can observe. Some theories, particularly those involving cosmic inflation, suggest that the observable universe is just one patch of a much larger cosmos, like a small section of a vast balloon. Different regions of this larger universe could have different curvatures, with our observable patch happening to be very close to flat. Testing such theories directly is currently impossible, as they involve regions beyond our cosmic horizon. But they raise the possibility that our measurements of cosmic geometry, even if perfectly accurate within our observable universe, might not represent the true global geometry of the cosmos as a whole. Beyond these practical challenges lie deeper questions about the limitations of measurement itself. Quantum mechanics, our best theory of the subatomic world, suggests that there are fundamental uncertainties in nature, not just limitations of our measuring devices. At the smallest scales, position and momentum cannot both be precisely determined simultaneously, a limitation known as Heisenberg's uncertainty principle. Some physicists have speculated about whether analogous limitations might apply to cosmology. Could there be fundamental uncertainties in our ability to measure the geometry of the universe as a whole? Might quantum effects at the earliest moments of the cosmos have introduced irreducible uncertainties in its overall shape? These questions remain speculative, but they suggest that some aspects of cosmic geometry might be not just practically difficult, but theoretically impossible to determine with perfect precision. Despite these challenges, astronomers continue to develop new techniques and instruments to probe cosmic geometry with ever greater precision. Future space missions will map the cosmic microwave background with unprecedented sensitivity, potentially detecting the subtle signatures of primordial gravitational waves that could reveal details about the universe's earliest moments. Ground-based telescopes will survey billions of galaxies, tracing the large-scale structure of the cosmos in 3 dimensions. Gravitational wave observatories will detect ripples in space-time from distant cataclysms, providing new windows into cosmic geometry. These efforts represent one of the greatest scientific adventures of our time, a quest to map the shape of everything despite the formidable challenges involved. They combine cutting-edge technology, sophisticated mathematics, and human creativity in an attempt to understand the fundamental geometry of reality itself. But perhaps the most profound implication of these observational challenges is philosophical. They remind us that our knowledge of the cosmos is always provisional, always limited by our perspective within it. We cannot step outside the universe to observe its shape directly. We must infer its geometry from within, using the light and other signals that reach us from distant regions. This inherent limitation echoes ancient philosophical questions about the relationship between appearance and reality, between what we can observe and what actually exists. We can build mathematical models of cosmic geometry that elegantly explain our observations, but we can never be absolutely certain that these models perfectly capture the true shape of the cosmos in all its complexity. The universe keeps its secrets well guarded, revealing its geometry only partially, through subtle effects that require immense effort to detect and interpret. Yet the fact that we can discern anything at all about the shape of the cosmos represents a remarkable achievement, a testament to human curiosity and ingenuity. Perhaps there is a certain beauty in this incompleteness, this cosmic reticence. If we could easily and definitively determine the universe's shape, the quest would end, the mystery would dissolve. Instead, we continue to probe and measure, to refine our theories and improve our instruments, engaged in an ongoing dialogue with the cosmos about its fundamental nature. This dialogue has already revealed far more than our ancestors could have imagined. From a universe that appeared to be centered on Earth, with perfect celestial spheres carrying the stars and planets, we have progressed to a cosmos of galaxies and voids, dark matter and dark energy, curved spacetime and cosmic expansion. We have measured the age of the universe to a precision of less than 1% and determined that its geometry is remarkably close to flat. These achievements represent not an endpoint, but a waypoint in our cosmic understanding. As we move forward, new observations will further constrain the shape of the universe. New theories will emerge to explain these observations, and new questions will arise from both. The observational challenges we face are not obstacles to progress, but opportunities for discovery, invitations to look deeper and think more creatively about the geometry of reality. As we drift towards sleep, let us appreciate both what we know about cosmic shape and what remains unknown. Let us hold in mind the image of the universe as a vast geometric structure, one that we can measure and model with remarkable precision, even as its fullest form remains partially hidden from view. In our next chapter, we will explore the philosophical implications of cosmic geometry, the meaning we might find in the shape of everything. But for now, let us rest in the wonder of a universe that reveals its form to us gradually, through light that has traveled across the vastness of space and time to reach our instruments and, ultimately, our minds. To grasp shape is to glimpse the universe's soul. Throughout our cosmic journey, we have explored the mathematics, physics, and observational evidence regarding the universe's shape. We have examined how this shape might evolve over time and influence the emergence of life. But beyond these scientific considerations lie deeper philosophical questions about what cosmic geometry means for our understanding of existence itself. In this chapter, we reflect on the philosophical implications of living in a universe with shape, a cosmos whose very form guides its destiny. The question of cosmic shape connects to ancient philosophical inquiries about the nature of space. From the earliest days of human thought, philosophers have debated whether space is a thing in itself or merely a relationship between objects. Is the void truly empty, or does it possess properties of its own? Does space exist independently of the matter within it, or is it merely an abstraction, a way of describing how objects relate to one another? The Greek atomists, like Democritus, conceived of atoms moving through an infinite, empty void. For them, space was nothingness, the absence of being, the stage upon which the drama of physical reality played out. Aristotle, by contrast, rejected the concept of a void, arguing that space was defined by the objects that occupied it, with no independent existence of its own. Modern physics, beginning with Newton, initially seemed to favor the atomist view, treating space as an absolute, fixed framework, independent of its contents. But Einstein's theory of relativity transformed this understanding, revealing space and time as dynamic entities, curved by the presence of matter and energy. In Einstein's vision, space is not empty nothingness, but a structured field with physical properties, capable of bending, stretching, and even rippling with gravitational waves. This conception of space as a physical entity with shape and structure represents one of the most profound shifts in human thought. It bridges ancient divides between being and non-being, substance and void. The emptiness between objects turns out not to be empty at all, but a geometric field whose properties influence everything within it. The philosophical implications of this view are vast. If space itself has properties, if the void is not truly void but structured and dynamic, then the ancient dichotomy between matter and emptiness dissolves. The universe becomes a unified whole, a seamless integration of substance and geometry, with neither reducible to the other. This holistic perspective resonates with certain philosophical traditions, particularly those of Eastern thought. Buddhist conceptions of emptiness, for instance, do not treat the void as mere nothingness, but as a pregnant potential, the ground of all being. Taoist notions of the Tao as an unnameable principle that guides all existence similarly echo the modern understanding of space as not merely empty, but structured according to mathematical principles that shape cosmic evolution. The unity of geometry and matter in modern cosmology also connects to the ancient Pythagorean belief that mathematics underlies reality. For the Pythagoreans, numbers and geometric forms were not just human inventions, but fundamental aspects of existence itself. Modern physics has revealed a universe governed by mathematical laws of astonishing precision and beauty, suggesting that the Pythagoreans glimpsed something profound about the nature of reality. But this raises a deep question. Why is the universe mathematical at all? Why does cosmic geometry follow consistent rules that can be described by elegant equations? The physicist Eugene Wigner famously called this the unreasonable effectiveness of mathematics in the natural sciences, the puzzling fact that abstract mathematical concepts, often developed without any reference to physical applications, turn out to perfectly describe the structure and behavior of the physical world. Some philosophers suggest that this mathematical character of reality indicates something fundamental about the universe, that it is in some sense a mathematical structure. Others propose that the mathematical nature of physics reflects the structure of human cognition, the ways in which our minds have evolved to model and predict the world around us. Still others, following Plato, suggest that mathematical forms exist in some ideal realm, separate from physical reality, but somehow connected to it. These different philosophical perspectives each offer ways of making sense of cosmic geometry. Is the shape of the universe an intrinsic property of reality itself, or a construct of human understanding? Is mathematical physics discovering the universe's true nature, or imposing a human framework upon it? These questions have no definitive answers, but they invite us to reflect on the relationship between mind and cosmos, between our conceptual models and the reality they represent. Another profound philosophical implication of cosmic geometry concerns the nature of time. In Einstein's theory of relativity, space and time are unified into space-time, a four-dimensional geometric structure. The shape of this structure determines not just how objects move through space, but how events unfold through time. This geometric view of time challenges our intuitive understanding of temporal flow. In space-time, all moments, past, present, and future, exist together in a single geometric entity. The present is not privileged over the past or future, just as no point in space is inherently more important than any other. Our experience of time, as flowing from past to future, may be more a reflection of human perception than a fundamental aspect of reality. Some philosophers, following Einstein's colleague Hermann Minkowski, embrace this view of block universe, where time is just another dimension in a static four-dimensional structure. Others argue that this picture misses something essential about the nature of time, that the distinction between past, present, and future reflects a fundamental asymmetry in reality, not just in human experience. The debate connects to ancient philosophical questions about being and becoming, permanence and change. Is the universe fundamentally static, with change being merely an appearance created by our limited perspective? Or is change, evolution, becoming an irreducible aspect of reality, with the geometric picture of space-time being an incomplete representation? The expanding shape of our universe, with its one-way evolution from a hot, dense past to a cold, diffuse future, suggests that asymmetric time may indeed be woven into the fabric of reality. The second law of thermodynamics, which states that entropy or disorder tends to increase over time, similarly points to a fundamental arrow of time, aligned with cosmic expansion. Yet modern physics still struggles to fully reconcile the time-symmetric equations of fundamental theories with the time-asymmetric character of thermodynamics and cosmology. The shape of the universe evolves in a definite direction, from past to future, but our deepest physical laws treat both directions as equivalent. This tension between reversible fundamental laws and irreversible cosmic evolution represents one of the most profound puzzles in our understanding of reality. The philosophical questions raised by cosmic geometry extend beyond space and time to the nature of existence itself. Why does the universe have the particular shape it does? Could it have been different? Is there some necessity to its geometry, or is it contingent, one possibility among many? These questions connect to what philosophers call modal metaphysics, the study of possibility, necessity, and contingency. If our universe is just one geometric configuration among many possible ones, as suggested by multiverse theories, then its particular shape might be contingent, the result of random processes in a vaster reality. But if there is some deeper principle that determines why the cosmos has the shape it does, then perhaps its geometry reflects some form of necessity, some constraint on what can meaningfully exist. Some theorists have proposed that the universe's shape optimizes certain mathematical properties, like maximum entropy or computational complexity. Others suggest that the anthropic principle provides a kind of explanation. The universe has the shape it does because that shape allows for the emergence of observers like ourselves who can contemplate it. Still others argue that the question why may be misplaced when applied to the universe as a whole, since any explanation would need to reference something outside the cosmos, which, by definition, encompasses all of physical reality. These reflections lead to perhaps the deepest philosophical question raised by cosmic geometry. What is the relationship between mind and the shape of everything? How is it that configurations of matter within the universe, namely our brains, can come to understand the very geometry of the cosmos that contains them? Is there something significant about a universe that can generate observers capable of comprehending its own structure? Some philosophers and scientists have proposed that consciousness might be connected to the universe in ways more fundamental than we currently understand. Quantum mechanics, with its emphasis on the role of observation in determining reality, has led some thinkers to suggest that consciousness might play a role in the very definition of physical reality. Others speculate that consciousness might be a fundamental property of the universe itself, not reducible to physical processes but somehow integrated with them. While such ideas remain speculative and controversial, they reflect a profound intuition that the relationship between mind and cosmic geometry might be deeper than that of mere observer and observed. Perhaps in understanding the shape of the universe is in some sense understanding itself through us, matter becoming conscious of its own geometric structure. Regardless of how we resolve these philosophical questions, the contemplation of cosmic geometry offers a unique perspective on human existence. We find ourselves within a vast, curved space-time, our every movement following geodesics determined by its shape. We are not separate from this cosmic geometry but integral to it, configurations of matter and energy whose very being is informed by the structure of reality. This integration of human existence with cosmic form provides a kind of cosmic belonging, a sense of our place within the architecture of everything. Unlike the pre-Copernican view, which placed humanity at the center of the cosmos, or the early modern view, which seemed to reduce humans to insignificant specks in a vast, meaningless void, the modern understanding of cosmic geometry suggests a more subtle relationship. We are neither the center of creation nor merely accidental byproducts, but expressions of a universe whose very shape has allowed for the emergence of life and mind. The universe's shape, understood this way, becomes not just a scientific or mathematical fact, but a context for meaning. The same curved space-time that determines the orbits of planets and the expansion of galaxies also cradles human existence, enabling the emergence of beings capable of wonder, curiosity, love, and understanding. The geometry that guides cosmic destiny also guides our own smaller journeys through space and time. This perspective invites a kind of philosophical humility. The shape of the universe vastly exceeds our direct experience, extending across billions of light years and evolving over billions of years. Our lives unfold within a tiny region of this immense geometric structure, our perceptions limited to a narrow slice of cosmic reality. Yet through science, mathematics, and philosophy, we can extend our understanding beyond these limitations, grasping at least some aspects of the universe's shape. At the same time, the success of human minds in comprehending cosmic geometry suggests a profound resonance between consciousness and reality. Despite our physical insignificance in cosmic terms, our capacity for understanding connects us to the universe as a whole. Through the structures of our minds, we can grasp the structure of everything, linking our inner worlds to the outer cosmos in an act of comprehension that spans the scales of existence. Perhaps this is the deepest meaning of cosmic shape, not just that the universe has geometry, but that this geometry can be known, that conscious beings can arise within the cosmos and come to understand the very form that contains them. In this sense, the universe's shape becomes an invitation to understanding, a structured reality that beckons conscious exploration. As we contemplate these philosophical dimensions of cosmic geometry, we may find ourselves experiencing what the philosopher Bertrand Russell called cosmic religious feeling, a sense of awe at the vastness and order of the universe, combined with a recognition of the human mind's capacity to comprehend at least some portion of this cosmic structure. This feeling transcends specific religious traditions but connects to the sense of wonder and meaning that has animated human spiritual quests throughout history. The shape of the universe, in this light, becomes not just a scientific question but a spiritual one, touching on our deepest yearnings for connection, understanding, and purpose. By exploring cosmic geometry, we place ourselves within a larger context, linking our brief lives to the grandest scales of space and time. We discover that we are not separate from the cosmic shape, but expressions of it, matter that has become aware of the geometry that contains it. As we drift towards sleep, let us carry with us this philosophical awareness, this recognition that in contemplating the shape of everything, we touch upon the deepest questions of existence. In our next chapter, we will explore how cosmic geometry has influenced human imagination and creativity, how the shape of the universe has inspired art, literature, and cultural expression. But for now, let us rest in the wonder of being conscious participants in a shaped universe, beings capable of grasping, however partially, the form of reality itself. Shape stirs the human spirit. Throughout human history, our understanding of cosmic shape has profoundly influenced culture, art, literature, and imagination. From ancient myths to modern science fiction, humans have sought to represent and make meaning from the geometry of the cosmos. As our scientific understanding has evolved, so too have our creative expressions of cosmic shape, reflecting our changing relationship with the universe that contains us. In ancient times, many cultures envisioned the cosmos as a series of concentric spheres or layers. The ancient Mesopotamians imagined the universe as a series of domed heavens above a flat earth. Greek thinkers, following Aristotle and Ptolemy, elaborated a model of nested crystalline spheres carrying the planets, stars, and celestial bodies around the Earth. These geometric models were not merely scientific theories, but cultural frameworks that influenced art, architecture, literature, and religious thought. Medieval European cathedrals, with their domes and arches, often embodied this celestial geometry, recreating the spherical heavens in stone and glass. The concentric circles of Dante's Divine Comedy, with its carefully structured realms of hell, purgatory, and paradise, similarly reflected the geometric cosmos of medieval thought. These were not abstract scientific concepts, but lived realities that shaped how people understood their place in the cosmic order. The Copernican revolution, which moved Earth from the center of the universe to just one planet orbiting the Sun, created a profound shift in human imagination. The cosmos expanded vastly in scale and complexity, challenging artists and writers to envision a universe without a clear center or boundary. This decentering of human existence provoked anxiety, but also wonder, as expressed in John Donne's famous lines. The new philosophy calls all in doubt. The element of fire is quite put out. The sun is lost, and the earth, and no man's wit can well direct him where to look for it. As telescopes revealed ever more distant celestial objects, the imagined shape of the cosmos continued to expand. The discovery of other galaxies beyond our Milky Way in the early 20th century further transformed our conception of cosmic scale and structure. The universe became not just a solar system or even a single galaxy, but a vast collection of island universes scattered across seemingly infinite space. Einstein's theory of relativity, with its curved spacetime and expanding universe, introduced new forms into the cultural imagination. Salvador Dali's melting clocks in The Persistence of Memory have often been interpreted as a response to Einstein's flexible spacetime, though Dali himself denied this specific influence. Nevertheless, the warping of space and time entered the broader cultural consciousness, creating new metaphors and imagery for artists to explore. Science fiction, perhaps more than any other genre, has embraced cosmic geometry as both setting and subject. Writers like H.G. Wells in The Time Machine and Edwin Abbott in Flatland explored the implications of time as a fourth dimension and the limits of spatial perception. Later authors like Arthur C. Clarke, Isaac Asimov, and Ursula K. Le Guin created vast future histories unfolding across galactic scales, their narratives shaped by the expanding and evolving universe revealed by modern cosmology. Stanley Kubrick's film 2001, A Space Odyssey, with its famous Stargate sequence showing psychedelic tunnels of light, attempted to visualize travel through warped space-time. More recently, Christopher Nolan's Interstellar worked closely with physicist Kip Thorne to create scientifically accurate depictions of a spinning black hole and its gravitational effects on space and time. These visual representations have helped make abstract cosmic geometry accessible to broader audiences. The multiverse concept has proved particularly fertile ground for creative exploration. Jorge Luis Borges, The Garden of Forking Paths, anticipated the many worlds interpretation of quantum mechanics with its vision of endlessly branching realities. Contemporary works like Michael Crichton's Timeline, Blake Crouch's Dark Matter, and the animated series Rick and Morty have popularized the notion of parallel universes with different physical laws and histories. In music, composers like Gustav Holst, with his Planet Suite, translated astronomical objects into sonic experiences. Modern electronic and ambient musicians often explicitly reference cosmic phenomena, creating soundscapes meant to evoke vast, geometric spaces. The composer Jean-Michel Jarre has performed concerts with visuals specifically designed to represent cosmic structures and geometry. Visual artists have likewise drawn inspiration from cosmic shape. Abstract expressionists like Jackson Pollock created works that some critics have compared to astronomical photographs of galaxies and nebulae. The artist Vija Selmins has meticulously reproduced starfield photographs, inviting viewers to contemplate their position within the vast cosmic web. Installation artists like Olafur Eliasson and James Turrell create immersive environments that alter perception of space, inviting reflection on how we experience geometric reality. Digital technology has enabled new forms of cosmic representation. Planetarium shows can now simulate flights through accurate three-dimensional maps of the known universe, based on actual astronomical observations. Video games like No Man's Sky and Elite Dangerous generate vast procedural universes for players to explore, their algorithms mimicking the processes that shape real cosmic structures. Virtual reality offers perhaps the most promising medium for experiencing cosmic geometry, potentially allowing users to viscerally experience non-Euclidean spaces or higher dimensions in ways previously accessible only through mathematical abstraction. Though still in early stages, VR experiences like Overview and Apollo 11 VR hint at how this technology might transform our ability to imagine and interact with cosmic shape. These cultural expressions of cosmic geometry serve important functions beyond entertainment. They help translate abstract scientific concepts into forms that can be emotionally and intuitively grasped. They create metaphors that connect cosmic scales to human experience, making the unimaginably vast relatable through narrative, image, and sound. And they explore the philosophical and existential implications of our evolving understanding of the universe's shape. For instance, the expanding universe, with its finite past and potentially infinite future, has become a powerful metaphor for possibility and openness. The cosmic web, with galaxies connected by filaments across vast voids, offers an image of interconnection despite apparent separation. The curvature of space-time provides a way to conceptualize how unseen influences shape our path through life. These scientific realities become cultural resources for meaning-making. The very fact that we can represent cosmic shape in art, literature, and other cultural forms speaks to something profound about human consciousness. We are not merely passive recipients of an external reality, but active interpreters who construct meaningful patterns from our observations and theories. Our cultural representations of cosmic geometry are not just reflections of scientific understanding, but creative extensions that explore possibilities beyond current knowledge. In this sense, science and art are complementary approaches to cosmic understanding. Science provides increasingly precise measurements and models of the universe's shape, while art explores the human meaning and experiential dimensions of those models. Together, they create a more complete picture of our relationship with cosmic geometry than either could alone. As we complete our journey through the shape of the cosmos, from its mathematical foundations to its cultural expressions, we return to a simple yet profound awareness. The universe changes shape, stretching and folding in ways beyond our immediate senses, and as it evolves, so too does our understanding, forever growing, forever mysterious. The universe we observe today is vastly different from its earliest configuration. In its infancy, it was a hot, dense plasma, every part causally connected to every other part, its geometry potentially very different from what we observe now. Today, it is cool, diffuse, and expanding at an accelerating rate, its shape approaching perfect flatness, even as its expansion stretches space ever thinner. In the distant future, billions and trillions of years hence, the universe may be almost empty from our perspective, with galaxies beyond our local group having receded beyond our cosmic horizon, their light unable to reach us against the tide of accelerating expansion. The observable universe will shrink even as the entire cosmos expands, creating ever more isolated islands of matter in an increasingly vast void. Or perhaps the nature of dark energy will change, altering the universe's evolutionary trajectory in ways we cannot yet predict. The cosmic geometry might transform dramatically if dark energy weakens, strengthens, or changes its character. The shape of everything remains dynamic, not fixed, its future evolution not fully determined by its present state. Our understanding of this cosmic evolution has itself evolved dramatically over human history. From a universe centered on Earth, bounded by celestial spheres, we have progressed to an expanding cosmos of galaxies and voids, curved space-time and quantum fields, its geometry shaped by dark matter and dark energy. Each stage in this intellectual journey has revealed new aspects of cosmic shape, new dimensions of reality previously unimagined. This evolution of understanding will surely continue. Future observations will refine our measurements of cosmic curvature, expansion, and structure. New theories will integrate these observations into more comprehensive models, potentially revealing aspects of cosmic geometry currently hidden from view. Questions that seem profound to us today may find answers, while new questions will emerge to challenge future generations. The shape of our understanding thus mirrors the shape of the cosmos itself, both always evolving, both combining stability with change. Just as the universe maintains certain fundamental principles even as it expands and transforms, our knowledge preserves core insights even as it grows and develops. Einstein did not negate Newton, but extended him. Modern cosmology does not erase ancient wonder, but contextualizes it. In this ongoing process of discovery, we participate in a remarkable cosmic phenomenon, the universe becoming aware of its own shape through conscious beings that have evolved within it. We are not separate from cosmic geometry, but expressions of it, configurations of matter and energy, shaped by the same principles that govern the cosmos as a whole. Our ability to comprehend the universe's form represents a kind of cosmic self-knowledge, reality reflecting upon its own structure. This awareness invites both intellectual humility and wonder. Humility, because we recognize how much remains unknown, how limited our perspective remains despite centuries of scientific progress. Wonder, because despite these limitations, we have discerned patterns and principles at cosmic scales, glimpsing the shape of reality far beyond direct human experience. As we drift now towards sleep, let us carry this dual awareness with us, this recognition of both what we know and what we do not. Let us appreciate the remarkable journey of cosmic understanding that has brought us to this moment, even as we recognize that this journey continues beyond us. Let us rest in the knowledge that we are part of an evolving cosmos, our minds temporarily aligned with its geometry, our brief lives contributing to its ongoing story. The universe changes shape, stretching and folding in ways beyond our senses, and as it evolves, so too does our understanding, forever growing, forever mysterious. In this dance of cosmic form and human comprehension, we find our place, not at the center of creation, but as conscious participants in its unfolding geometry, as beings capable of asking questions about the shape of everything and finding, if not final answers, then meaningful patterns that connect us to the vast architecture of existence. Sleep now, and dream of curved space and expanding time, of galaxies dancing along cosmic filaments, of light bending around massive objects, and quantum fields vibrating in multiple dimensions. Dream of a universe whose shape includes you, whose geometry accommodates consciousness, whose evolution has produced beings capable of wondering about it all. And perhaps, in those dreams, you may touch some aspect of cosmic form that waking thought cannot reach, some intuition of the shape of everything that transcends our current understanding. For in the end, the universe is not just something we observe, but something we are. Its shape is not just external to us, but runs through us, defining the possibilities of our existence. In contemplating cosmic geometry, we contemplate ourselves, matter that has become conscious of the form that contains it, stardust reflecting on the shape of everything,